So read the question along with the figure. Determine the natural frequency of torsional oscillation for the following system. The system is a reciprocating IC engine coupled to a centrifugal pump through a pair of gears. Okay, so you have an engine on the left. So engine flywheel is your rotor A. Okay, don't worry about the reciprocating masses. You have only the flywheel A. Okay, so from the flywheel you have a shaft which is getting connected to a gear. That pinion gear E is going to drive a wheel. See here, he has marked as pinion here, but that is not correct actually. So driving should be pinion. This is wrong. Okay, so this is your E is your pinion and this is your gear wheel. Okay, so you can even refer your design subject handling people, they will tell you, right? So now that is not important for dynamics anyway, I am telling you generally. Okay, so determine the natural frequency of torsional oscillation for the following system. System is a reciprocating IC engine coupled to a centrifugal pump through a pair of gears. The shaft for the flywheel engine to the gear wheel is of diameter 60. So this is 60 millimeter from the engine to the gear. Okay, driving gear length is 950. Shaft from the pinion to the pump is 40 diameter and 300 mm length. So diameter is 40, length is 300 mm. The engine speed is 1/4 of the pump speed. So you will get a gear ratio of 1/4. Correct? So, sorry, 1/4 only. So engine speed is 1/4 divided by 1. Okay. So this means what? The pump is running very fast. Correct. Engine speed is 1/4 of the pump speed means what? Pump is running fast. So therefore your N, you will see that G, how to do G that. So of the pump speed. So these are the data given to you. Moment of inertia of the flywheel is 800. Okay, moment of inertia of the gear usually gear we neglect, but here it is also given to you 15. Pinion wheel is given to you 4. In the moment of inertia of the pump disc at the end, this is your pump, B is your pump. So 17. Modulus of rigidity C is given 84. Okay, so list down the given data. So gear ratio is 1/4. How? So omega A by omega B. What is omega A? 1/4 divided by 1. So motor speed is 1/4 of the pump speed. Pump is very fast. So if we bring it up, then also we will get only 1/4. Clear? There should be no confusion here. So D1 from the engine to the gear is 60 millimeter. The length of that portion is 0.95 meter. D2 is 40 millimeter. The length of that portion is 300. So this is your engine flywheel moment of inertia, driving gear moment of inertia, driven gear moment of inertia, and your centrifugal pump impeller moment of inertia, modulus of rigidity. All the things are given to you. Okay. Just a minute. The original and the equivalent systems are shown below figure. Okay, so we are eliminating the gears and adding the torsional resistance to the rotor at the end, and I am going to call that as B dash. Same procedure. Okay, but since you are considering the inertia of these gears, you cannot altogether eliminate them. That like what you used to do in the previous problems. So we are going to put a rotor here also. It becomes a 3-rotor problem. Clear? When does it become a 3-rotor problem? When you consider the inertia of the gears. You cannot eliminate this totally. Okay, you cannot eliminate this totally. If you consider the inertia of the gears also, then you have to do it as a 3-rotor problem. Okay, therefore this remains same, only this will vary. Clear? Okay, because you are considering the inertia of the gears, it becomes a 3-rotor problem. So this also is called equivalent gearing. So this is E, this is E dash. I am replacing it with the rotor, dynamically equivalent rotor. Okay, so E is replaced with E dash, B is replaced with B dash. Okay, so first of all, find the moment of inertia of the equivalent gearing E, equivalent pump B, and the additional length of the shaft with the equivalent shaft diameter, first diameter D1, 60 millimeter. Okay, moment of inertia of the equivalent gearing E equal to the first gear remains same, the second gear only the diameter is changing, right? So second gear diameter is adjusted here. So first gear there is no change in the shaft diameter, 60 is 60. Second gear only the shaft is changing. Therefore, I am adjusting that IF by G square. Clear? 15 plus 14 by 0.25 square. So 79. So in such problems, you make a note of this formula. Okay. So for replacing the gear systems, driving is kept as it is. The driven is divided by the speed ratio. That is your general formula, square of speed ratio. So 15 is the amount of inertia of the driving gear. 14 is the amount of inertia of driven gear. Gear ratio is 1 by 4, which is 0.25. So if you do this, solve this, you will get 79 as the moment of inertia of this setup. Equivalent gearing. What is equivalent gearing? It is replaced with a rotor here, which is having a moment of inertia of 79. It creates an equivalent amount of torsional disturbance in this equivalent shaft. Okay, right. So moment of inertia of the equivalent pump B. So same formula here. IB dash. This is the old formula that we used to do usually. Same whatever you have did in the last problem. IB dash equal to IB by G square. Okay. So 17 by 0.25 square, which comes around 272 kilogram meter square. Okay. So L3 formula. This also you know. Same formula. G square into L2 into D1 by D2 whole power 4. Okay. So G is 0.25, L2 is 0.3, D1 is 0.06, D2 is 0.04. This is D2. 40 millimeter. Correct. D2. So put it into that formula. So G square into L2 into D1 by D2 whole power 4. I am putting all the numbers. I am getting 0.095 meter as the extra length beyond the first shaft in the equivalent configuration. Okay. So all the things are found out. The original system is reduced to a 3 rotor system as shown below. Right. Let us find the position of the nodes for the equivalent system. Any doubts up to this? Why I am having a third rotor E dash? Because you are considering the inertia of the gears. I am replacing it with an equivalent rotor E dash, whose thing you have found out, inertia you have found out, IE dash equal to IE plus IF by G square. So let LA equal to distance between the node and rotor A. So it has completely nothing to do with these two figures. LA will be visible only in the strain energy diagram, the third diagram below this. So one important thing I forgot to mention you, these diagrams will not be in the question paper, but you have to draw it in the exam. Diagrams carries mark. I forgot to mention that so far. So these diagrams you have to draw. Okay, maybe shorter or maybe longer. The second one, the length is not important. Okay, maybe if I draw, I don't know whether it will be shorter or longer. So I may draw the second diagram longer than this. That is not a problem. You can do any length, but you have to draw it. Okay. So let LA equal distance of the node N1 and rotor A. LB is the distance of the node from the rotor B. Single node configuration. 3 rotor system. Okay. If 3 rotor system, then you have another problem. You will have both single node and 2 node conditions. Because these two can be rotated in same direction and this may be rotated in the opposite direction. Okay, these two in the same and this in the opposite will result in single node configuration. But if you do these two in the same and this in the opposite, you will result in a 2 node condition. We have seen all these things in detail previous classes. All the videos are available. Go and check it. Okay. So we know that LA IA equal to LB dash IB dash. So LA, I am going to find out an equivalence between LA and LB. So LA value is 800, IB is 272, IA IB. Okay, so LA equal to LB dash into. So this using this relationship, this formula, I am finding out a relationship between using this. I am substituting the values of moment of inertia only, and I am ending up with the relation. So LA equal to 0.34 LB dash. Okay, wherever you have LA, you are going to substitute LB dash there. You are going to eliminate LA out of the calculation. Okay. So LA equal to 0.34 LB dash. This is 3 rotor configuration. Okay. What you usually used to write 1 by LA equal to 1 by IB into. Similarly, that middle portion, whatever B used to be in the middle in a 3 rotor problem usually. Okay. So A, B, C. Whatever is in the middle, that will have this type of a format. Now B is not in the middle. Now E is in the middle. Okay. So usually in all the 3 rotor problems, this will be your A, B, C. So for the middle format, you write like this. Instead of 1 by LB IB, you will write 1 by IB into 1 by L1 minus LA plus 1 by L3 minus LB. But here E is in the middle, so same B format of formula is applied to E. Okay, so 1 by IE dash into 1 by L1 minus LA plus 1 by L3 minus LB dash. Right, L3 is your equivalent shaft extra length after the first portion of the shaft. See, if you do not know the previous problems that we did in the last class, this will be a little bit difficult for you to understand. I suggest you go back to do the 3 rotor problems, then come here, you will easily understand this. All the videos are available to you. I shared it in your classroom and the WhatsApp group also. Okay, have a look at it, and then if you see this video also will be shared. Then you look at this, you will understand. Okay, the same for whatever method we have been using till now for a 3 rotor problem, same method I am using. Okay, so in place of LA you put 0.3 for LB. Okay, so I know that LA equal to 0.3 for LB. So here instead of LA I am writing 0.3 for LB dash. Okay, so I have eliminated LA out of this. Only LB dash is unknown, so I am going to find the LB dash out of this. Clear? So rearrange this, take LCM, cross multiply. I will end up with a quadratic equation: 1.44 LB dash square minus 1.325 LB dash plus 0.026 equal to 0. If you do not do this calculation, you cannot know whether it is correct or not, right? You have to solve this, take LCM, multiply, take common factor outside, everything, and then adjust it and get this equation. Okay, because this is a PPT, I am not doing all that. You have to do it with your hand. Please do it, try it. Okay, so I am getting a quadratic equation. Now I am going to find the roots of this equation. So I will have two possible values of LB, two roots of the equation, quadratic equation. Take your calculator, you can find the roots of this equation. Okay, so by the formula method, if you see what is the formula for finding the roots of a quadratic equation, I'm going to write down this is the formula: minus b plus or minus root of b square minus 4. You can directly do it in the calculator, you don't have to do this. Okay, so I know, so coefficient of square component is a, so I'm going to take a as 1.44. Coefficient of the LB dash is b. Along with the symbol, if you have negative, you have to take. So minus 1.325 I'm taking. Okay, so C component 0.026. Because you have positive symbol here, no need to take the symbol. Put all these three values into this equation. Okay, you will find out the two roots of the equation. So minus b plus or minus root of b square minus 4ac by 2a. I will end up with two roots, 0.9 or 0.02. Both roots are positive. Okay, so now I know that LA equal to 0.34 LB dash. Okay, therefore I can easily find out LA. So LA equal to 0.34 into 0.9 or 0.34 into 0.02. The two values of LB and substitute. So either this value or this value. So you will get two probable values of LA. So 0.306 or 0.0068. So this will be your single node configuration because the length is very large. So this will be your two node configuration since the value is very small. Okay. So hence single node position, LA is the larger length you take for single node. Okay, so LA is 0.306, LB dash is 0.9. So two node position, smaller values, 0.068 and the corresponding value of LB 0.02. What is the condition? If I multiply 0.34 here, I should get this answer. Similarly, 0.34 you multiply here, you should get this answer. So that is your condition. Okay. So two node configuration value diagram is given here. Single node configuration diagram is not there. You can go back to the three rotor problems and see that. Okay. So polar moment of inertia of the shaft, I am considering the first diameter as the equivalent diameter. Okay. 60. This is my D1, 60 mm. Therefore, I am going to put 60 here. So 0.06. Polar moment of inertia is 1.27 into 10 power minus 6 meter power 4. Okay. So natural frequency, any one formula you can solve. Now we have two probable values of LA. So we will end up with two frequencies. Single node frequency, two node frequency. Larger value is for single node frequency. Okay, so C is 84 into 10 power 9, J is 1.27 into 10 power minus 6, LA is 0.306, IA is 800. Put all these values into this. Now this is your single node configuration because the value is longer. Okay, your strain energy diagram will be like this. Okay. For the next condition, your two node condition, your strain energy diagram will be like this. So here the two rotors A and E will be rotated in one direction, and the last rotor will be in a different direction. Here both the extreme rotors will be in same direction, the middle rotor will be in a different direction. That is the reason for two node and single node configuration. Okay, so wherever you can blindly take larger value of length, the other value of LA is what? 0.0068, smaller value. You take it for two node condition. It's larger value you take for single node condition. Okay, so put all the numbers into this. So this is your C, J, LA, IEA. Solve it, you will get 3.32 Hz natural frequency of single node configuration. Okay, so single node frequency of torsional vibration FN1 is 3.32 Hz. Similarly, the second case, take the another LA, all the other values are same, no change. Okay, so C is same, J is same, LA only changes 0.0068, IA is same. Put all the numbers into the square root. So same thing, you will get 22.3 Hz. So this is a two node torsional frequency. Hence natural two node torsional frequency of the vibration is 22.3. So that completes the problem. So we will summarize the results. So location of the node on a single node configuration. What is the location of the node? Give LA and LB. So 0.306, LB dash is 0.9. So the frequency of that LA and LB is 3.32 Hz. Single node configuration. So two node configuration, LA is 0.0068, LB is 0.02. Okay. So how it will be looking like? If this is so small value, you have 1 meter shaft, how it is possible? So it means what? Your node is very close to one end here, and the other node is here. This is how your two node configuration will look. Therefore, this is 0.0068, this is 0.02, whereas the actual shaft length is around 1.2 meter. Okay, so this is your rotor A. The nearest node from rotor A is 0.0068 meter. So some around 6.8 millimeter. Similarly, from here it is 2 millimeter. 20 millimeter. So the remaining in the middle is in a different direction strain energy, negative or positive, based on what you are considering for the extremes. Clear? So therefore, location of the two node configuration nodes is LA is 0.068. One node is from the left, one node is 6.8 millimeter. From the right, the second node is 20 millimeter. Okay. So frequency of that configuration, torsional vibration, is 22.3 Hz. So it is taken from your Kurmi textbook, 24.10 example problem. That is the last problem in your third